Hello everyone and welcome to a new episode of All Things IDA. In today's episode we're going to talk about hook notification points. This is an important concept in IDA because it allows us to collect events from different subsystems in IDA. For example, receive events from the processor module, from debuggers, from graphs, from the decompiler as well, from the database, custom viewers, and so on. This is an essential topic because it will allow us to do more things in IDA programmatically for the future. With that, let's get started. Okay, so today's session is gonna be mainly theoretical. Of course, I'm gonna talk about code and so on, but it's important to understand concepts first at a higher level. So at a higher level here, I made this illustration and we can think of the notification points as a way to orchestrate events. We have the IDA kernel, which is IDA DLL or IDA64.dll, which is the central to everything. This is where we can install notification points or hooks so we can receive those notifications, and as well we can dispatch, for example, through a function called callui and so on. But mainly let's focus on receiving events and hooking to those events. So IDA kernel being the central component here, we can then think of notification sources coming from different subsystems, I'm gonna call them. So for example, we can receive events from the processor module. Things like an instruction is being decoded or EV underscore analyze instruction. Or we can even get notified when an instruction is about to be emitted. And so if we receive that event, we can intercept it and then change the behavior, for example. Other sources of events we can hook to, for example, are debuggers. Let's say we want to receive certain events from the debugger, we can hook to the debugger source, and then we can receive things such as debug start process, breakpoint, load library. The graph, for example, we can listen to events coming to graphs, whether the IDA built-in graph viewer or even user graphs, which we haven't spoken about yet. You can build your own graphs in IDA. And we will receive events, respond to the events. Maybe IDA will ask us, hey, how to draw that node, what's the text? Receive the event, we fulfill the event. We can think of this almost like window messages, for example. Similarly, a rich source of events is the UI events. There are hundreds of those events we can listen to. And usually, for example, we can receive an event about a window being opened or closed, change of focus, a key is pressed, database is saved, UI is ready, and so on. The database events, we can also hook to what we call ht_idb source, and then we can receive events such as database has been closed or opened, it's been saved, and so on. We can also augment the output window by listening to the HT output events. So we can receive double clicked, clicked, key presses, and so on. So we can augment the output window functionality. In the same fashion, the decompiler as well has the same mechanism where plugin writers can also install hooks, what Hexrace here calls Hexrace callbacks, but it's the same concept where we insert our handler. We can have many listeners. We will get a chance to receive that event and act upon it. So we're gonna go over all those different sources of events, and we're gonna first start with how to install a hook, and then we're gonna go over a bunch of examples of those event source generators. Alright, so as usual, we're gonna start with the SDK, and in order for us to install events, we are gonna look in ida.hpp at a function called hook to notification point. The hook to notification point is how we can install our callback. It needs the hook type, or let's say the source of the events. So we have the debugger and the graph and so on. We specify it here. Our callback function and a user data that we will receive back in our callback. So this is useful. Let's say if your callback is in a class, you can pass the user data as the this pointer, so you can access your class members and make your hook a bit more stateful instead of being just globally and static and so on. So let's take a look at the hook types. So I did mention the hook types or sources here in this diagram, but if we look at it programmatically, it's in the hook underscore type underscore t, and we have here all different classes of hooks. So we have the IDP hooks, IDA processor module hook. This will give us processor events. So let's take a look at some of those events. So we're gonna go to idp.hpp and look for processor event. So this is the enum, simply they're numeric values that we will receive in our callback. For example, we can receive ev init that the processor module has just initialized, and it will receive a parameter. Here the parameter is the processor name, which is a string. We're gonna take a look at the callback itself in code, just to show you how we can retrieve this information. Terminate, for example, the processor module is unloaded. The user switching the processor module, changing the assembler syntax, creating a new file. We can receive then the file name. Old file has been loaded, so we can distinguish if a new file has been created or an old file has been opened. When an instruction is being decoded, hopefully in the future we get to talk about processor extensions, so we can augment the processor, and mainly this is of use. We can augment the decoding abilities of the processor module. So if there's a missing instruction, we can hook this event. We get the chance to interpret the bytes and disassemble them. In IDA's terms, this is called analyzing an instruction, hence the EV event, analyze instruction. As well, this is also mainly focused in the realm of the processor module development. So emulate an instruction, we get to analyze what the instruction does with respect to cross-references, tag variables, and so on. So this is here the logic. We can intercept and augment the logic here, for example. Stuff related to outputting a mnemonic, outputting the instructions, so we can even change the way the disassemble renders things by simply hooking those events. Now, I'm gonna switch back and show you just one callback, and then we continue visiting the other types of hooks. Take a look at the hook callback. So we said it takes the hook type, which can be any of those sources. We looked at the processor module hook type. But first, let's take a look as well at the callback itself. So how does the callback look like? Well, the callback is a function that returns a number. And here we have the explanation, what those numbers mean. 0, that we simply got a copy of the event, but we want to pass it down to the next handler. We return 0, and returning non-zero can mean many things, but usually non-zero means that we handle the event, so do not further dispatch it. So the hook itself will receive back the user data we passed here. So this is important, that you can have context within your callback. You will receive the code itself depending on the hook type. So if we're looking at the processor module stuff, we will be looking at these numbers. These are the hook types, over here notification codes. And then we get variadic argument list. And this is where we'll use the std_arg.h to extract further arguments based on the notification code itself. So let's take a look at the code and install a couple hooks. Okay, so here I prepared a piece of code, basically just a plugin, the usual construction. So we inherit from plug mode. Now don't mind this at the time being, this is a convenience. We inherit from plug mode as usual, and let's focus in on the constructor to begin with. So in the plugin constructor, we install a hook. For example, the hook type is processor module events, and we pass the hook, the callback, and the context or the user data, which is the this pointer. So let's go to the callback here. So this is the callback. It has the same signature as required, which is the user data, the notification code from that hook type. So we'll get, in this particular one, we'll get processor module events, and the VA list. We might have 0 arguments for that specific notification code. We might have more. So let's take a look in this example. So what did I look for in this hook? So I installed the hook. This hook will receive all the events in that particular hook type. Then it's up to you. So the usual construct is we're going to use a switch and select on the code. If you have multiple notification codes you handle, it's best to use a switch, otherwise if else is enough. So in this here, in this callback, I care about generating a map file. I want to intercept when generate map file is invoked from the UI. So let's take a look here at the sources. So this will take us to idp.hpp one more time. And this is how we can interpret the documentation. So we have all the event codes here. This is the beginning of the event codes. And based on the event itself, we will see in the documentation, for example, what it means. It's called like that and so on. And then we will see the parameter here. And the order is important. So options, which is const char pointer, and confidence for this event, for example. So going back to the map file, you see it's generate a map file. Then if it's not implemented in the processor module, then the kernel will make something generically. But this is where you can actually augment that functionality. If a given processing module doesn't know how to generate a map file, or you're not satisfied with how that map file is generated, you can hook, listen to that event, and then simply return to the kernel. So for the generate map file, we can see it takes the first argument is the number of line, which is int pointer, and it will give you a file handle already, the file pointer. So how do we retrieve that from our callback? That's simple. We will receive, as we said, the VA list, and to use the VA list, well, here it is indirectly included, but we will use the header file stdarg, and then here we will be using the VA arg. We'll pass the VA, and this will help us retrieve one of the variadic arguments. So the first one is an int pointer, which is described here. And the second one is a file pointer. We simply retrieve those arguments and off we go. We can act upon them, and if we want, we can return one of the proper return values per that code. But generically, 0 means, for the kernel perspective, in general, means simply continue dispatching. Non-zero can mean different things per the event itself. So here I always return 0, so I am a passive listener to those 4 events. Ev new file. Now you don't have to extract the arguments, only if you need them. So you can simply receive the notification code, and you don't have to do anything. You say, okay, I received the event. So let's see new file. New file, for example, receives the file name. Now I simply display a message and be done with it. But if I wanted to retrieve that, I would have to do the same thing. So normally I'll have to take, for example, character pointer here, fname equals va arg, va, and this one. And now I have the fname. If we mess up the orders and so on, we will have undefined behavior, potentially crashes. So that's how we interpret the events. It's gonna be the same for any kind of hook type and for any kind of notification code. We will receive what those notification codes dictate in their documentation, and we should obey the return values. That is the gist of it. So now I'm gonna be walking around the different hook types, different notification codes, and discussing some high-level ideas. Let's take a look at the graph, and the graph is in graph.hpp, and the codes are grcode underscore. So let's go to graph.hpp and look for grcode underscore, and here they're under the enum graph notification underscore t. And here we can receive as well graph events. For example, the graph has been clicked, and we will receive which graph component, which graph view. That's the visual aspect of it. This is a parameter we can use with other APIs. If it needs, let's say, to close that widget, we can pass that pointer and so on. And we receive the selection item. This usually should be enough information for us to know where stuff has been clicked. When a group is being created in the graph, when a group is being deleted, when the user text, so when we are about to render the graph text, we can intercept that. We will receive the data element of the graph, the node ID, and an output character pointer. So we can tell IDA this is what we want to display for that specific node ID, for example. So there are many graph events we can look at. Next is the user interface hook types. And this is special in particular because it's 2 kinds of functionality we can retrieve. We can listen to events, we can invoke user interface stuff, and we can do both at the same time. So here, when we look at the notification codes for the HTUI class, so here now we're looking at the HTUI class, we have those notification codes. In the kernel documentation, we can see that we have UI colon. These are events marked like that. That means we can call them, so we can invoke those UI functionalities. But the kernel doesn't really host any user interface. When we use the IDA SDK, we can call MSG, we can call warning, we can show a user form, ask using form. We can do various UI stuff from the kernel, and one might wonder, does the kernel actually implement the UI? No. As you notice, the UI is almost uniform with respect to the kernel. The kernel works in text UI, graphical interface, maybe headless, and so on, all by the ability to delegate the UI responsibility to the UI subsystem through callui. So it will, the kernel, we ask the kernel, hey, I want to display a message. The kernel will issue a callui function call, and then and the callui function call, it will use one of those UI marked events. We'll see clearly what are stuff we can receive just to listen to as events. They will be marked with CB colon, or things we can call. Now usually things we can call we can also listen to, but not everything we can listen to we can call. So some events are passive, we just receive them. Some events we can issue through the call UI. We can see here, for example, a read selection. If we want to read the selections from the kernel, which doesn't have any UI understanding, we can call the function read selection, which eventually will end up using call UI, passing this notification code with the arguments. So let's take a look at how UI events are invoked rather than listened to, because here we can see the marker UI colon. That means this can be used in call UI. So let's look at call UI. So call UI, as you can see here, it is a callback function. It is important to know that this pointer is initialized by the host. So it could be either Qt, so either Qt based interface, or the either text interface, or even your own host, for example, as we shall see in the future. So whoever sets that callback is gonna be responsible for handling the UI subsystem in IDA. Now we don't have to worry about who sets it. We can assume either it's the IDA text or the IDA Qt interface that initialized that pointer. So all we have to do is simply invoke it. So when we say call UI and the notification, it will be intercepted by the host, the graphical host, and rerouted to the actual implementation of the UI stuff. So when we're looking for read selection, let's see how read selection is implemented. It's gonna go through the call UI to dispatch that. So read range selection invoked as a kernel function, but is gonna be dispatched like this. So we're gonna pass the notification code, and it says, okay, if you want to call the UI subsystem from the IDA kernel, you're gonna use call UI with this event code, and these are the arguments. And these arguments, if you are on the receiving side, this is what you will extract from the VA list. You will receive the widget, you receive the two output arguments for the selection, the start and end, for example. So call UI is very important, and you should know the call UI pointer is implemented in the IDA host. This is a very important concept. So let's scroll through the UI notifications. Here we can see, for example, UI range, the disassembly range has changed. So the min EA and max EA have changed. Let's look for something useful. For example, UI is saving, database has been saved. This is a callback. So we receive, for example, where the database has been saved. Let's say you want to implement a plugin that takes a backup each time you save the database. Takes a backup to the network, for example. You can hook and listen. So you hook to the HT_UI type and listen on the notification called UI_saved. And then you will receive one argument, what has been saved. And here the return value is ignored with the return 0 or 1. It seems the kernel doesn't care. So normally we would return 0 because we have to return a value from the callback of hook notifications. Other things that we will see in the future are things like the populating menus. So for example, we will be sometimes needing to have a plugin when we right click in IDA, we want to add a new item, a pop-up menu item when we right click. So we can then listen to UI populating widget pop-up. That's one of them. IDA will issue this callback. We can see here it's a CB, it's a callback, and will tell us what graphical component, so the widget is the graphical component, what's the pop-up handle, and what's the activation context. So this is in reference to the actions video I mentioned in the past. Because we receive those, we can then use a supplementary function from inside the callback to add the menu. So once we receive UI populating widget pop-up, if we want to add a pop-up to augment the existing pop-up menu set, we have everything we need to use the secondary functions, for example, attach action to pop-up. We can use this function. We have already received the widget from the callback itself. We have received the pop-up handle from the callback itself. All we have to do is simply what's the name and the location of the new pop-up item we want to add, for example. And so this is how we can augment IDA, and we should put this into practice in future episodes. And so there are hundreds of UI events, and this is really the richest one of them. So these are the UI elements. Now that you know the basics, you can explore those events and be creative on how to use them, when to use them, and so on. So let's continue. We have the debugger control as well. So we can receive debugger events if we look at dbg.hpp. we have dbg notification, and we can receive things such as debug process start, and this will give us one argument, the debug event, which will contain various things about the process start debug event. Process exit, breakpoint. If we hook and listen for that notification code, we will receive the thread ID under which the breakpoint has broke, and the address, and an output parameter we can decide the behavior, for example. Step over, or step into, these events finished, took place, you can receive them. So every time there's a step, you can get called, and when you're called, you can log them, for example, or wait for a certain address and act upon it, and so on. We have the ht_idd, so there's a difference, it's important to note. So we have htdbg, which is I call the debugger control, that will let us listen to the debugger actions, or we can call those actions as well, but this is where we can control the debugger. And we have another one for the debugger, which is htIDD. Now, this is where we create a debugger. This is where the kernel will interface with our actual debugger plugin. If you're writing a new debugger plugin, you have to implement a set of events that the kernel will call whenever the user wants to step into. Then the kernel will issue a specific htIDD event, and you have to implement that event. For example, read memory. The kernel will say, hey, I want to read the memory. So it will issue an event to the htIDD class, and it will dispatch it. You receive it in your debugger. We will have in your debugger construction, you will have a callback where you receive those events, and you have to implement event read, for example. Let's take a quick look here. So this one is in idd.hpp, and here are the events that you as a debugger writer, so here if you look to the parent, it's inside the debugger structure. This is when you write a debugger. You will receive those events and you have to implement them. So for example, if you receive the event init debugger, that means the kernel is asking you as a debugger plugin to initialize yourself. Attach, then you're supposed to be attaching. You will be receiving the process ID and event ID and so on, so you can carry that action. So those are different than the DBG notifications. So normally this is for the consumer, where you receive those, and IDD is where you implement those. More things worthwhile mentioning is the output window. So we can augment IDA's output window. So as well here, we can look at current win, at the MSG click events. So here we have the parent enum. And as the output window in IDA, you can augment the output window by intercepting one of those events. So you can tell when the user double clicks on the output window. So let's say you want to augment the double click. So when the user double clicks on certain string, you do certain action. Maybe you copy it to the clipboard. Normally IDA, when you double click on something, if it's a number, it tries to jump to that address. Or if it's an identifier, it tries to jump to its location. You can augment that functionality. You can intercept key presses. You can also intercept if the output window has been closed or activated or deactivated. The custom viewers as well, same story. You can have things like IDA view, but you can populate it with your own things. So the disassembly view, you can have similar functionality using custom viewers, which we will talk about in the future. The IDB is worthwhile noting as well. These are database events. Let's take a look at ht_idb. Here, idp.hpp and the IDB events. So these events, you can receive things that are immediately useful to you. You can be creative what to do with it. For example, you receive a closed database. You can maybe deinitialize your plugin or something. Also, of course, your plugin, if it has the proper flags, then it will be automatically destructed when the database closes. But maybe you want to have that notification before your plugin is, or the database has been unloaded. So this is before we're closing. It will be closed. It's not closed. So maybe you can capture some information before the database closes. The database has been saved. Database has been upgraded. Let's say you're switching to a new version of IDA and you had your own net nodes. And now lots of changes happened. You want to receive that event that IDA data structures in the database changed. Maybe you also want to upgrade your internal storage in the net nodes, for example. You can tell when the analysis is over. So auto analysis queue is empty. That means like IDA's idle. When main has been discovered, for example, this is when you're loading a file for the first time, IDA still analyzing. You can get notified when main is determined. External language change. So if you're switching from Python to IDA, IDC or any other external language, you get notified, so you as well can do things there. Signature loaded, if the user loads a signature, you can get notified what signature has been loaded, so maybe as well your plugin can change its behavior. Type information changed, enum has been renamed. So in the past, people did some kind of collaborative IDA experience where they captured most of the IDB events and they dispatched them through the network to another IDA client. Like this gives the impression of collaborative IDA, where one user is doing something, it's propagated through the network to another user. They have been using those kinds of events to know when these things happen. A structure is being renamed, structure is expanded, segment has been added. So there's enough event to capture almost every small action that you're doing in IDA. You could be serializing those things, for example, noting them in the file, logging them, and so on. So function tail deleted, function tail appended, code has been created, data has been created, identifiers has been renamed, a patch happened. So this is really useful for capturing the interaction database, whether they happen via DUI or not. We can now talk about the decompiler. Now, the decompiler is not really part of the IDA kernel, but the concepts are the same. So the decompiler itself is a plugin, but it also exposes its own APIs and then you can use it. Now we spoke about the decompiler in the past. We're just gonna mention the same concept as hook notification points, but from the decompiler's perspective. So in the decompiler, they are called install hexrace callback, remove hexrace callback, and these will allow us to install a callback and listen for decompiler events. And of course, there's a finite set of events we can interact with. So let's take a look at the decompiler events. So here we're gonna need the hexrace.hpp header file, and we're gonna say install hexrace callback. And this is our starting point. Install hexrace callback and remove hexrace callback. Same story. We're gonna now here we're not specifying a hook type because it is implied in the name. So when we install hexrace callback, we're gonna receive hexrace decompiler events, and we're gonna put the callback. You'll notice the callback will have the similar prototype. So we will have the user data, we're gonna receive back our user data, we're gonna receive the event number or the notification code, what hexrace event took place, and variable list of arguments. Depending on the event code, we can act and receive the information. So the hexrace event, these are the things we can receive. So they are prefixed with hxe underscore. So for example, here we can wait for when the flowchart has been generated. We receive a flowchart. You can see one of my videos. We spoke about the flowchart and basic blocks. Stack change points have been calculated. We will receive the microcode basic block array and the stack points here. When the prologue analysis has finished, when the microcode has been generated, block level optimization event. And some of them will be as well, not just non-visual, there will be also visual events. Here, user interface related events. For example, a new decompiler window has been opened. We may want to keep track of that widget for other purposes, to install menus or something. When we're switching from one pseudocode window to another, when we're refreshing, so you get another chance to as well recompute your supporting data. You can intercept keyboard events. So let's say you want to add some stuff, some more keys. You can get the keyboard events and as well do some actions when the user presses some keyboard stuff. So these are not necessarily the same as actions and hotkeys. These are really just keyboard events, A, B, C, D, etc. When the user right clicks, you will as well know that a right click in particular happened. Here they make sure that if you really want to add menu items, you should wait for the populating pop-up event. A hint is created, you want to augment the hint functionality, you will receive that event, then you can populate the hint string here. It's an output parameter. You can also have some kind of collaboration plugin. You can wait for those events like type changed, so you can propagate that through the network. Local variable command changed, comments got changed, and so on. You can then send it to the network if you're making a basic collaborative or some kind of real-time tracking of events. So this is the decompiler. Now finally, I'm gonna talk quickly about Python and show you the equivalent of those things in Python. One thing to note back, let's go back to the hook to notification point. The way it works is you need the hook type and the callback and the user data. The callback is variable argument list, and this poses a channel for the swig wrapper. So now, if you don't know what I'm talking about, you should see one of the videos about the IDAPython internals. But because of that limitation and difficulty to really wrap this with swig, the code that we can use for hook notification points in Python differs. Instead of having a switch and receiving a notification code in Python, we'll have a whole class with the supported events that Python will receive. So we should be able to see that in the example. So let's first take a look at the example. Let's say we want to do UI hooks. So in the UI hooks, what we have to do, instead of say hook to notification point, ht underscore UI, the callback, and user data, in Python, we have to subclass UI underscore hooks. And then for the notification codes, the UI underscore populating widget popup or UI underscore saving and so on, we have virtual functions, so to say, functions that we can override if we want to add our own functionality. For example, here, populating widget popup, you don't have to do what we did in C++. So going back here where we were using the VA list, retrieve the arguments like that. In the IDAPython wrapping, you receive them as a regular argument. So this is a bit more Pythonic and easier to understand. We simply subclass a class and override certain methods. So there are so many hooks. For example, we have UI hooks, IDP underscore hooks, and so on. Let's go to the IDAPython sources here in the IDA installation in Python, and we can look at the swig wrapper generated code. So the UI hooks, it will give us all of those hooks. So UI hooks, debug hook, hexarrays hooks, they will have the same methods to begin with, the hook and the unhook. And then we will have the events per notification code. So for example, suspend event, save database event, you receive the pass, database closed, debugger menu changed, so you will receive the enable disable, widget closing, which widget, get item hint, you will receive those things. For example, for the debugger events, same story, we're gonna have the debugger hook, which will have hook and unhook, and then we override the methods of interest, so we can override debugger process start and it will receive the PID, TID, and so on, and write our own code, debug process exit, and so on. And they will be the same for hexarrays and so on. So you can look at the online documentation for that, or you simply go to the IDAPython here in the IDA installation folder in Python 3, and dig into those generated Python files and look for something underscore hooks. You will find the hooks. And we have a limited set of hook classes, as we said. We have just these sets. Alright, so that's it for today. I think we covered the basics of hook notification points. We spoke about important aspects of hook notifications, the different kinds of hook types or the hook providers, so processor modules, the database, debuggers, and so on. We spoke about callui and the ability to have the IDA kernel as a generic interface, and then if it needs UI elements, it dispatches this request to the host, the graphical host, IDA text, IDA Qt, or a custom host. And we also covered the decompiler as well and how we can listen to decompiler events. Alright, I hope you found this useful. It will serve us in the future. Thank you and see you next time.